Hello friends, welcome back to my channel and welcome to this deep dive session on the internal structure of the Earth, plate tectonics and earthquakes, one of the most important, most predictable and most consistently asked topics in UPSC Mains GSI. This topic appeared in UPSC Mains 2025 as a difficult question on tectonic shifts. Most aspirants could not answer it well. By the end of this session, you will not just answer it, you will nail it. We are going to cover everything: the four layers of the Earth, the five major discontinuities, seismic waves, continental drift, seafloor spreading, all three types of plate boundaries, earthquakes and their measurement, volcanoes and the ring of fire, the Himalayan orogeny, India's seismic zones, and a complete answer writing framework for UPSC. Notice the four statistics on screen: seven major tectonic plates, great earthquakes reaching magnitude 7 to 9 on the Richter scale, the Gutenberg discontinuity at 2,900 kilometers depth, and the Earth's total radius of 6,371 kilometers. These four numbers alone will appear in your UPSC answers multiple times. So let us begin our journey from the surface of the Earth all the way down to its solid iron core. Here is a quick overview of our 10 modules for today's session. We will build knowledge systematically. Each module feeds into the next, creating a complete, interconnected understanding. We start with the internal structure, understanding what lies beneath our feet. Then we look at seismic waves, the instruments that helped us understand that structure. Module 3 gives us the grand plate tectonics theory, followed by the three types of plate boundaries in Module 4. Module 5 covers earthquakes in depth, cause, measurement, India's seismic zones. Module 6 takes us to volcanoes and the dramatic ring of fire. Module 7 explains how fold mountains like the Himalayas were born. Module 8 is our India special, all the governance, policy, and disaster management dimensions that make this topic relevant for GS1 and GS3. Module 9 gives you the UPSC writing strategy, previous year questions, and high value data. And Module 10 ties everything together in a concept map for rapid revision. Each module is exam ready. Let us move to Module 1. Module 1, the internal structure of the Earth. How do we know what lies inside the Earth when no one has ever drilled deeper than about 12 kilometers? The answer lies in seismic waves, and that is what makes this topic so fascinating. Let us start with the layers themselves. Look at the cross-section diagram on the left side of this slide. The Earth is structured like an onion, four concentric layers, each with distinct properties. Let us go from the outside in. The outermost layer is the crust, thin, brittle, and the only layer we actually live on. Now, there are two types of crust, and this distinction is critical for UPSC. Oceanic crust is thin, just 5 to 10 kilometers thick, and it is made of sema, silicon, and magnesium in the form of basalt. It is dark, dense, and heavy, with a density of about 3 grams per cubic centimeter. Continental crust is much thicker, 30 to 70 kilometers thick under major mountain ranges, and it is made of SiAl, silicon, and aluminium in the form of granite, lighter, paler, less dense at about 2.7 grams per cubic centimeter. The boundary between the crust and the next layer is called the Mohorovičić discontinuity, or Moho for short. It marks a sudden increase in seismic wave velocity from 6.9 to 8.1 kilometers per second. We will talk about this more in the discontinuities slide. Below the crust lies the mantle, the thickest layer, stretching from about 70 kilometers to 2,900 kilometers depth. The mantle itself has sublayers. The upper mantle includes the lithosphere at the very top, which is the rigid outer shell of the Earth formed by the crust plus the topmost mantle. Below the lithosphere is the asthenosphere, a semi-fluid zone of soft rock that flows very slowly, and it is this asthenosphere that allows tectonic plates to move. Deeper still is the transition zone at 400 to 700 kilometers, where minerals undergo phase changes. Olivine transforms to spinel, then to perovskite, and the lower mantle from 700 to 2,900 kilometers is solid due to immense pressure despite being hot. At 2,900 kilometers, we cross the Gutenberg discontinuity, named after Benno Gutenberg, and enter the outer core. This is liquid, a churning sea of molten iron and nickel at temperatures of 4,000 to 5,000 degrees Celsius. The convective currents in the outer core are responsible for generating Earth's magnetic field through the dynamo theory, and crucially, S waves cannot pass through liquid. The fact that S waves stop here is the proof that the outer core is liquid. And finally, at 5,100 kilometers, we cross the Lehmann discontinuity and reach the inner core. Despite a temperature of 5,000 to 6,000 degrees Celsius, hotter than the surface of the sun, the inner core is solid. Why? Because the pressure here is 3.6 million atmospheres, so enormous that the atoms cannot move freely even at that temperature. The inner core is an iron nickel alloy, about 1,270 kilometers in radius, and it actually rotates slightly faster than the rest of the Earth, a phenomenon called inner core superrotation. 4 layers: crust, mantle, outer core, inner core. Remember these with their depths, compositions, and states. Now let us focus on the boundaries between the layers, the discontinuities. These are the zones where seismic wave velocities change suddenly, telling us we have crossed from one material to another. The first is the Conrad discontinuity at about 20 kilometers depth within the continental crust. It separates the upper granitic crust from the lower basaltic crust, not found everywhere, sometimes absent, named after Austrian geophysicist Victor Conrad. The second and most important is the Mohorovicic discontinuity, always called the Moho, at about 35 kilometers under continents, just 5 to 10 kilometers under oceans. This is the boundary between crust and mantle. Seismic wave velocity jumps suddenly here. Discovered by Croatian scientist Andrija Mohorovicic in 1909 from earthquake data. The Moho forms the basis of the theory of isostasy, the gravitational equilibrium of the crust floating on the mantle like ice on water. The third is the Repetti discontinuity at 400 to 700 kilometers, the transition zone between upper and lower mantle. Minerals undergo phase changes here. This is why we sometimes see two separate discontinuities labeled the 410 kilometer and 660 kilometer discontinuities. The fourth, and most dramatic, is the Gutenberg discontinuity at 2,900 kilometers. This is where S waves completely disappear. They cannot enter the liquid outer core. P waves are also refracted significantly, discovered by Benno Gutenberg in 1914, also called the core mantle boundary or CMB. And the fifth is the Lehmann discontinuity at 5,100 kilometers, discovered by Danish seismologist Inge Lehmann in 1936. She noticed that some P wave signals were arriving in the shadow zone, which could only happen if there was a solid inner core refracting them. She is the only woman to have discovered a major discontinuity within the Earth. For UPSC, remember all five: Conrad, Moho, Repetti, Gutenberg, Lehmann, in order of depth. Each has a discoverer, a depth, and a significance. Module 2: Seismic Waves and Evidence. We said the Earth's interior is revealed by seismic waves. But how exactly? There are three types of seismic waves, and each one tells us something different about the Earth's interior. Let us look at them one by one. There are three types of seismic waves: P waves, S waves, and surface waves, each with completely different properties. Let us go through them systematically. P waves, primary or compressional waves. These are the fastest seismic waves, traveling at 8 to 14 kilometers per second through the mantle. They work like a sound wave, pushing and pulling the rock in the same direction as the wave is traveling. This is called compressional or longitudinal motion. The crucial property of P waves is that they can travel through solids, liquids, and even gases. This means they can pass through the liquid outer core. They arrive first at a seismograph. That is why they are called primary. There is a shadow zone for P waves between 103 and 145 degrees from the earthquake focus on the other side of the Earth. This shadow zone exists because P waves are refracted, bent, as they cross the core mantle boundary. The shape and size of this shadow zone told seismologists precisely where the core begins. S waves, secondary or shear waves. These are slower, 4 to 7 kilometers per second. They move the rock perpendicular to the direction of wave travel, shaking it up and down or side to side like a snake wriggling. This is called transverse or shear motion. The critical property of S waves, they can travel only through solids, they cannot pass through liquids. When S waves hit the liquid outer core, they stop. The fact that no S waves are detected beyond 103 degrees from the focus is direct proof that the outer core is liquid. This is one of the most elegant pieces of scientific detective work in geology. Surface waves, or L waves, are the slowest of all but the most destructive. They travel only along the Earth's surface. There are two types: love waves, which shake the ground horizontally like a snake, and Rayleigh waves, which roll like ocean waves in an elliptical motion. These waves have the largest amplitude, the biggest ground movement, and cause the most damage to buildings. They arrive last at a seismograph. Here is the UPSC key point about all three. The time gap between P wave and S wave arrival at a seismograph tells us how far the earthquake focus is from that station. And if we have three seismograph stations, we can triangulate and pinpoint the exact epicenter. That is how every earthquake location is determined. Module 3: The Theory of Plate Tectonics. We have understood the structure of the Earth. Now we understand the movements of the Earth's outer shell. How do continents move? Why do mountains form where they do? Why do earthquakes and volcanoes concentrate in specific zones? Plate tectonics answers all of these questions with one elegant theory. The story of plate tectonics begins with a German meteorologist named Alfred Wegener, who in 1912 proposed the most revolutionary and at the time most ridiculed theory in geological history: continental drift. Wegener looked at a world map and noticed something remarkable. The eastern coast of South America fits perfectly into the western coast of Africa, like two pieces of a jigsaw puzzle. He proposed that all the continents were once joined in a single supercontinent he called Pangaea, meaning all earth in Greek. Pangaea existed about 250 million years ago, then broke apart into Laurasia in the north and Gondwanaland in the south about 180 million years ago and gradually drifted to their present positions. His evidence was extraordinary. Identical fossils, the freshwater reptile Mesosaurus and the plant Glossopteris, found on both sides of the South Atlantic, separated by thousands of kilometers of ocean. If these creatures could not swim across the Atlantic, how did they end up on both continents? The only explanation: the continents were once joined. He also found matching rock strata, rocks of identical age and composition on both sides of the Atlantic, and climate evidence: coal seams formed in tropical forests found in Antarctica, glacial deposits found in tropical Africa. This could only make sense if these landmasses had moved dramatically, but Wegener had one fatal flaw in his theory. He could not explain the mechanism, the force that actually moved the continents. He proposed polar fleeing force and tidal forces, neither of which was strong enough. The geological establishment rejected his theory completely for decades. He died in 1930 before his ideas were vindicated. The vindication came in 1960 when American geologist Harry Hess proposed sea floor spreading. Using newly developed sonar technology from World War II, Hess discovered that the ocean floor was not static. New oceanic crust was being created at underwater mountain chains called mid ocean ridges, where hot magma welled up from the mantle, cooled, and pushed the older crust aside. This was confirmed by the magnetic stripes on either side of mid ocean ridges. symmetric bands of normal and reversed magnetism that record the Earth's magnetic field reversals through geological time, like a tape recorder of the ocean floor creation. Sea floor spreading provided the mechanism Wegener could not. Continental drift plus seafloor spreading plus modern seismology together became the unified theory of plate tectonics in the 1960s, one of the greatest scientific achievements of the 20th century. Module 4, Types of Plate Boundaries. The Earth's lithosphere is broken into 7 major plates and 8 minor plates. Wherever these plates meet, extraordinary geological events happen: mountains rise, trenches form, volcanoes erupt, earthquakes strike. There are 3 types of plate boundaries, and each creates a completely different set of landforms. 3 types of plate boundaries. Let us go through each one in detail, with examples that will anchor these in your memory. Type 1, Convergent boundaries, where plates move toward each other. This is where the most dramatic and destructive geological processes happen. When an oceanic plate meets a continental plate, the oceanic plate, being denser, goes under the continental plate in a process called subduction. This creates deep sea trenches, chains of coastal volcanoes, and fold mountains. The Andes Mountains formed exactly this way, the Nazca Oceanic Plate subducting under the South American continental plate. When 2 oceanic plates meet, one subducts under the other, creating deep trenches and chains of volcanic islands called island arc. Japan, the Philippines, and the Aleutian Islands are all island arcs. The deepest point on Earth, the Mariana Trench at 11,034 meters, formed at an ocean ocean convergent boundary. When 2 continental plates meet, neither is dense enough to subduct, so they collide and the crust crumbles and is pushed upward, creating enormous fold mountain ranges. This is exactly how the Himalayas formed, the Indian plate crashing into the Eurasian plate. This is the most relevant boundary for India. Type 2, Divergent boundaries, where plates move away from each other. New crust is created here as magma wells up from below. Under the oceans, this creates mid ocean ridges, the world's longest mountain chain at 70,000 kilometers, mostly hidden under the sea. The Mid Atlantic Ridge is the most famous. Iceland is a volcanic island that sits directly on the Mid Atlantic Ridge. You can actually stand at the boundary between 2 plates there. On land, divergent boundaries create rift valleys where the crust pulls apart and sinks. The Great African Rift Valley is the world's best example, stretching 6,000 kilometers from Ethiopia to Mozambique. The Red Sea itself is a young ocean being born. The Arabian and African plates are pulling apart, and in millions of years, the Red Sea will be as wide as the Atlantic. Type 3, Transform boundaries, where plates slide horizontally past each other. No crust is created or destroyed, just ground and shattered. These generate the most powerful and most shallow earthquakes. The San Andreas Fault in California is the most famous. The Pacific Plate grinding past the North American Plate at about 5 centimeters per year. The 1906 San Francisco earthquake was a transform boundary event, and critically for recent events, Turkey's North Anatolian Fault is a transform boundary. The devastating February 2023 earthquake of 7.8 magnitude that killed 50,000 people was a transform fault rupture. India specific note at the bottom: the Indian plate is still colliding with the Eurasian plate at 5 centimeters per year. The Himalayas are still rising. This is why Nepal, Uttarakhand, and Himachal Pradesh have frequent, powerful earthquakes. The tectonic story of India is not finished. Module 5, Earthquakes. Approximately 500,000 earthquakes occur every year. About 100,000 are felt by humans. About 100 cause significant damage, and about 20 are truly major. Understanding earthquakes, their causes, measurement, and impact is essential for UPSC, not just for GS1, but for disaster management in GS3 as well. Let us master the key terminology of earthquakes. Every one of these terms is directly examined in UPSC, focus, or hypocenter. This is the point inside the Earth where the earthquake energy is released. It is the starting point of the seismic waves. Earthquakes are classified by their focus depth. Shallow focus, 0 to 70 kilometers, are the most destructive because the energy reaches the surface quickly without dissipating. Intermediate focus earthquakes are 70 to 300 kilometers deep. Deep focus earthquakes are 300 to 700 kilometers deep. They release enormous energy but less surface damage because the waves travel so far. Epicenter, the point on the Earth's surface directly above the focus. This is the point of maximum intensity. Isoseismal lines, lines of equal seismic intensity, are drawn concentrically around the epicenter. The epicenter is determined by triangulating PS wave arrival time differences from at least three seismograph stations. Magnitude, measured on the Richter scale, developed by Charles Richter in 1935. This measures the energy released at the source. It is a logarithmic scale. Every increase of 1 unit means 10 times more ground displacement amplitude and approximately 31.6 times more energy released. So a magnitude 8 earthquake releases 31.6 times more energy than a magnitude 7. Modern seismologists prefer the moment magnitude scale MW, which more accurately measures very large earthquakes. Intensity, measured on the modified Mercalli scale using Roman numerals from 1 to 12. This measures the effect at a specific location, how strongly it was felt. Intensity varies with distance from the epicenter, local soil conditions, and building quality. It is subjective, unlike magnitude, which is objective. Seismograph, the instrument that records seismic waves. Its recording is called a seismogram. Based on the principle of inertia, a heavy mass on a frame stays relatively still while the Earth moves around it. Invented by John Milne in 1880. And tsunami, perhaps the most feared effect of underwater earthquakes, generated by sudden vertical movement of the ocean floor during submarine earthquakes, volcanic eruptions, or underwater landslides. Tsunami waves travel at 800 kilometers per hour, as fast as a jet aircraft, but are barely noticeable in the open ocean. They amplify dramatically as they enter shallow coastal waters. The 2004 Indian Ocean tsunami, triggered by a 9.3 magnitude earthquake off Sumatra, killed 230,000 people across 14 countries. India's INCOIS, Indian National Center for Ocean Information Services, operates the Indian Tsunami Early Warning Center since 2007. India's seismic zonation is a critical topic for UPSC. It appears in both GS1 and GS3 questions about disaster management. The Bureau of Indian Standards has divided India into four seismic zones based on the expected intensity of ground shaking. Zone 5, very high risk. This covers the entire northeast India: Assam, Manipur, Mizoram, Meghalaya, Arunachal Pradesh, Tripura, Nagaland. The most seismically active region in India. Also covers Jammu and Kashmir, including parts of Ladakh, Himachal Pradesh, Uttarakhand, the Kutch region of Gujarat, and the Andaman and Nicobar Islands. Three devastating events: the 2001 Bhuj earthquake in Gujarat, 7.7 magnitude, 20,000 deaths; the 2005 Kashmir earthquake, 7.6 magnitude; and the 1950 Assam Tibet earthquake, 8.6 magnitude, the largest ever recorded in India. Zone 4, high risk. This includes parts of Jammu and Kashmir, Himachal Pradesh, Delhi NCR, Sikkim, North Bihar, Haryana, Chandigarh, West Bengal, and parts of Maharashtra near the Latur region. The 1993 Latur earthquake, 6.2 magnitude, 10,000 deaths, was a wake up call about intraplate seismicity in supposedly moderate risk areas. Zone 3, moderate risk. Parts of Kerala, Goa, Karnataka, Maharashtra, Rajasthan, Tamil Nadu, Odisha, and Jharkhand. The 1967 Koyna Dam earthquake, 6.3 magnitude, occurred in this zone and is the most important example of reservoir induced seismicity in India. Zone 2, low risk, most of peninsular India, the stable Deccan Plateau, southern Karnataka, Tamil Nadu coast. Old rigid cratonic rocks are less susceptible to seismic activity, but note, even Zone 2 is not zero risk. The critical UPSC fact at the bottom of this slide, approximately 59% of India's land area lies in zones 3, 4, and 5. 38 cities with more than 5 lakh population are in high damage zones. And Indian Standard IS 1893 prescribes earthquake resistant construction, but compliance remains poor, especially in rural areas. Module 6, Volcanoes and the Ring of Fire. If plate boundaries are the stage, volcanoes are the most dramatic performers. Let us understand the types of volcanoes, their distribution, and why India, a country not usually associated with volcanic activity, has its own volcanic heritage that UPSC students must know. Volcanoes are classified by activity into three types, and the India specific examples here are directly UPSC relevant. Active volcanoes are currently erupting or have erupted recently. About 1,500 active volcanoes exist globally. Famous examples: Mount Etna in Sicily, Italy, the world's most active volcano; Kilauea in Hawaii, essentially continuously erupting since 1983, and critically, Barren Island in the Andaman and Nicobar Islands, the only active volcano in India. It last erupted in 2020. It is a stratovolcano, also called a composite volcano, with steep sides and explosive eruptions. Dormant volcanoes have not erupted in recorded history but are not considered extinct. They can erupt again. Mount Vesuvius, which destroyed Pompeii in 79 AD, is technically considered dormant and is one of the most dangerous volcanoes in the world because millions of people live near it. Mount Fuji in Japan is also dormant. Narcondam Island in the Andaman chain is India's dormant volcano. Extinct volcanoes show no signs of activity and are not expected to erupt. Aconcagua in the Andes, the highest mountain in the Americas, was once a volcano. And the Deccan Traps of India, that vast basaltic plateau covering much of Maharashtra, Karnataka, and Andhra Pradesh, represents perhaps the most dramatic volcanic episode in India's geological history, formed by massive fissure eruptions 65 million years ago. The Deccan Traps coincide with the Cretaceous mass extinction that wiped out the dinosaurs. The Ring of Fire. This is the dramatic horseshoe shaped belt around the Pacific Ocean, about 40,000 kilometers long. It produces 90% of the world's earthquakes and contains 75% of the world's active volcanoes. The Pacific Plate is being subducted under surrounding plates on all sides, creating trenches, island arcs, and coastal volcanic mountain ranges all around the Pacific Rim, from New Zealand through the Philippines and Japan, across the Aleutians, down through Alaska, and along both coasts of the Americas to the Andes. And a quick India specific note: Lonar Crater Lake in Maharashtra, sometimes mistakenly called volcanic, is actually formed by a meteorite impact approximately 50,000 years ago. It is a saline lake and has important scientific value. It is not volcanic. Do not confuse it with volcanic features. Module 7, Fold Mountains and Tectonic Landforms. The Himalayas are the world's youngest and highest mountain range. But how did they form, and why does this matter for UPSC? Because the Himalayan orogeny, the birth of the Himalayas, connects plate tectonics, climate, the Indian monsoon, river systems, and even the political geography of India. Let us trace this story from 250 million years ago to the present. Follow the timeline on screen. We are tracing 250 million years of geological history in about 3 minutes. 250 to 180 million years ago, the supercontinent Pangaea breaks apart. The southern half, Gondwanaland, includes what will become Antarctica, Australia, Africa, South America, and the Indian subcontinent, which at this time is a separate island landmass in the southern hemisphere. 180 to 140 million years ago, the Indian plate begins its long journey northward, moving at a geologically rapid pace across what was then the Tethys Sea, the ancient ocean that separated India from Eurasia. 65 million years ago, the Indian plate is near the current position of Madagascar. The Deccan Trap eruptions begin, perhaps triggered or amplified by the final stage of the Indian Plates movement. This is the same time as the mass extinction that killed the dinosaurs. 55 to 50 million years ago, the collision. The Indian plate crashes into the Eurasian plate. The Tethys Sea is squeezed and eventually closes completely. The sediments at the bottom of the Tethys Sea, layers of limestone and shale formed from marine organisms, are crumpled and pushed upward. This is the first phase of Himalayan uplift. This is why we find marine fossils, ammonites, belemnites, seashells at the top of Himalayan peaks. They were once at the bottom of an ocean. 35 to 20 million years ago, the main Himalayan thrust, rapid and dramatic uplift. The greater Himalayas, including Mount Everest, reach their current extraordinary heights. The ongoing compression also forms the Tibetan Plateau, the world's highest and largest plateau, and pushes ranges as far away as the Hindu Kush and the Karakoram. The present, the Indian plate is still moving northeast at 5 centimeters per year. The collision has not stopped. The Himalayas are still rising at about 1 centimeter per year. Mount Everest grows about 4 millimeters per year, and this ongoing compression causes frequent powerful earthquakes in Nepal, the Indo Gangetic Plains, and northeast India. The gold facts at the bottom of this slide are pure UPSC gold. Himalayas are fold mountains, not volcanic. K2 is in Pakistan occupied Kashmir, not in India proper. Marine fossils in the Himalayas are the proof of their oceanic sediment origin. Memorize all four. Module 8, India and Tectonics. The GS1 Special. This is where we connect the science to governance, policy, and disaster management, making this topic relevant for both GS1 and GS3. Let us look at 6 critical dimensions of India's tectonic challenges. Let us examine each of the 6 boxes on this slide. Each one is a potential UPSC question in itself. Reservoir-induced seismicity, or RIS. When a large dam fills, the weight of the water increases the stress on underground rock formations. This can trigger earthquakes even in areas not normally seismically active. The Koyna Dam earthquake of 1967, 6.3 magnitude in Maharashtra, is the most significant example of RES in India and one of the most important globally. Today, India has 177 large dams in high seismic zones. The National Dam Safety Act of 2021 was enacted precisely to address these risks, and the National Dam Safety Authority was established. Intraplate earthquakes. Why peninsular India is not safe despite being in zone 2 or 3. The Deccan Plateau has ancient buried fault lines, the Narmada Sun lineament, the West Coast Fault, that can reactivate. The 1993 Lata earthquake, 6.2 magnitude, 10,000 deaths, occurred in the supposedly safer Marathwada region. Most deaths were caused by heavy stone masonry construction that collapsed completely. This taught us that soft alluvial or laterite soils amplify shaking, and construction quality matters enormously. Urban vulnerability. 38 Indian cities with populations over 5 lakh lie in zones 4 and 5. The Indian Standard IS 1893 2016 prescribes earthquake resistant construction norms. But only about 20% of Indian buildings comply with these standards. Rapid, unplanned urbanization with poor enforcement is creating a time bomb of vulnerability. Early warning systems. India's National Seismological Network has 115 seismograph stations operated by IMD and NDMA. No technology currently exists to predict earthquakes, only to measure and warn after they begin. However, for tsunamis, India's INCOIS operates the Indian Tsunami Early Warning Center in Hyderabad since 2007, which can issue warnings within 20 minutes of a submarine earthquake. The NDMA guidelines on earthquake disaster management outline the 4 phases: mitigation, preparedness, response, and recovery. Northeast India, the most seismically active region in India, where the Indian plate, Eurasian plate, and Myanmar microplate all converge. The 1950 Assam-Tibet earthquake of magnitude 8.6 remains the largest earthquake ever recorded in India. It was so powerful that the Brahmaputra River changed its course. The region's seismic risk is compounded by the rapid development of large hydropower projects, multiple dams being built in high risk zones simultaneously. Institutional framework. The National Disaster Management Authority was established under the Disaster Management Act of 2005. The National Disaster Response Force, 12 battalions, provides the operational response capability, and India is a signatory to the Sendai Framework for Disaster Risk Reduction 2015 to 2030, the global framework that commits India to reducing disaster mortality, disaster affected populations, and economic losses. Connect this to SDG 11 on resilient cities and SDG 13 on climate action for a complete multidimensional UPSC answer. Module 9 UPSC Mains Writing Strategy. We have built your knowledge. Now let us sharpen your ability to use that knowledge in an exam hall. Previous year questions, high value data points, and a complete 6-step answer framework. Everything you need to write a top scoring mains answer. Look at the previous year questions box at the top. These are the actual questions UPSC has asked from this topic over the last 12 years. 2025 had tectonic shifts as a rated difficult question. Most aspirants fumbled it, but after today's session, you should be able to connect tectonic shifts to Himalayan formation, ongoing plate movement, earthquake zones, and governance responses. 2023 asked about factors responsible for Himalayan formation and their impact on India's climate. This requires connecting orogeny to monsoon, river systems, and biodiversity. 2019 asked about tsunami mechanisms and early warning systems, which you now know completely. 2013 asked for the internal structure of the Earth with a diagram. Now you can draw and explain all 4 layers and 5 discontinuities. Now the high value data points in the middle section. These 10 facts should be memorized and deployed in your answers. Earth's radius is 6,371 kilometers. Inner core radius is 1,270 kilometers. 90% of earthquakes in the Ring of Fire. Mariana Trench is 11,034 meters, the deepest point on Earth. Himalayas rise 1 centimeter per year. India moves northeast at 5 centimeters per year. 1950 Assam earthquake, 8.6 magnitude, largest in India. 59% of India's land in zones 3 to 5. Barren Island last erupted 2020. Deccan traps formed 65 million years ago. Now, the 6-step answer framework at the bottom. Step 1. Introduction. Define the topic with a striking line plus 1 key statistic. Do not start with the internal structure of Earth is. Instead, Earth's interior, structured in 4 concentric layers across 6,371 kilometers, holds the answers to why mountains rise, seas open, and continents drift. Step 2. Mechanism. Walk through the scientific process systematically. Layers or seismic evidence or tectonic cause, depending on the question. Step 3. Types and classification. Always classify. Boundaries, wave types, volcano types, earthquake types. Step 4. Regional examples with India focus. UPSC values India centricity. Always bring in Indian examples, Indian plate, Himalayan orogeny, barren island, seismic zones. Step 5. Contemporary dimension, climate change and glacial lake outbursts in Himalayas, RIS from dams, urban vulnerability, Dam Safety Act 2021, recent earthquakes. Step 6. Conclusion, NDMA plus Sendai framework plus SDG 11 and SDG 13. End with a forward-looking sentence. Look at the concept map on screen. At the center, Earth structure and tectonics, radiating outward. All 8 dimensions we covered today. Internal structure, seismic waves, plate boundaries, fold mountains and orogeny, earthquakes and tsunamis, volcanoes and ring of fire, climate change linkages, and India and policy. This is the image I want you to carry with you. These 8 dimensions are not separate topics, they are one interconnected system. Tectonic plates move because of convection in the mantle flows because of heat from the outer core is liquid because of Earth's composition and formation. Earthquakes happen at plate boundaries, volcanoes erupt where plates subduct or diverge, mountains rise where plates collide, rivers form where mountains rise, monsoons are influenced by mountain barriers, agriculture depends on monsoons, economies depend on agriculture. Earth science is not a dead subject of rocks and layers, it is the foundation of everything we see around us. Every mountain, every river, every earthquake, every farm, every flood. Master the science of the earth, and you master the foundation of all Indian geography. This is ESHIKSHABYBRAJESH, educating India one topic at a time. Thank you for watching. If this session helped you, please like, share, and subscribe to ESHIKSHABYBRAJESH. The next session in this geography series will cover ocean currents, ENSO, and climate systems, the natural sequel to both this video and our Indian monsoon session. All the best for UPSC Mains 2026. You have got this.